Okay, so let's go ahead and look at number 7. This one's a little bit different. If we read the directions for questions 7 through 10, select the vial that is needed to fill each order with the required number of milliequivalents of potassium chloride, and then calculate the volume to be withdrawn from the selected vial. So first we need to find the vial we want to use, and then we need to find the volume. Okay, so looking at the vials, the first one's got 5 mils in it. The second one, the first one has 10 milliequivalent. The second vial has 20 milliequivalent. The third has 30 milliequivalent, and then the fourth has 40 milliequivalent. What we're wanting to do is we need to add 14 milliequivalent of potassium to the patient's IV solution. All right, so we need to find out which one is going to work the best. The 10 milliequivalent, that strength is too low, and the other two look a little too high. Those are 40 and 30. 20 is just slightly higher than 14. So it's going to have more than enough that we need to use, so that is going to be the vial that we select, the 20 milliequivalent. Now if we look, it's 20 milliequivalent, but it's important to keep in mind that it's 2 milliequivalent per ml. So we're taking the vial that has 20 milliequivalent in it, but it's 2 milliequivalent per milliliter. That's the most important part to remember. Okay, so now we have our information ready to set up our proportion. We found the vial. We're using the 20 milliequivalent vial. Now we need to find the volume. So again, volume, milliliters. That's what we're going to be solving for now. So that's going to be our X. Always looking for our desired requested dosage, and that's 14 milliequivalent. And the available formulation, it's 20 milliequivalent, but it's 2 milliequivalent per mil. Okay, so now we're ready to solve for X. These are going to cancel themselves out. The milliequivalents will cancel themselves out. So 14 times 1 is 14, divided by 2, X equals 7 ml. All right, let's look at number 11. How many milliequivalents of potassium chloride are in 8 milliliters of solution? So the question has been flipped. We're not looking for milliliters anymore because they've given that to us. We're trying to find out how many milliequivalents there are. So that is going to be our variable this time. So if we look at the package, we can see that it's 30 milliequivalent, but it comes 2 milliequivalent per ml. And that's what we need to know to set up our proportion. Okay, so our X is going to be in milliequivalents. That's our variable. That's what we don't know. Desired milliliters are 8. The available formulation, 2 milliequivalent per 1 milliliter. Okay, so normally you're used to looking at these on the bottom, but in this case it's flipped because this time this is what we're trying to find. So we're ready to solve for X. The 8s are going to cancel out. The milliliters are going to cancel out. 8 times 2 is 16. Divide that by 1. X equals 16 milliequivalent. Okay, let's do one more like this with its, when it's reversed. How many milliequivalents of potassium chloride are in 15 mLs of solution? Okay, so again, they're giving us the solution and the volume already. So what we need to find are the milliequivalents. Now, if we look at the label, it says potassium chloride, 40 milliequivalents, but it comes 2 milliequivalent per ml. And again, you have to get used to kind of looking for that. It's usually almost always right next to the strength of the vial. So we're looking for milliequivalent. That's going to be our X, our variable. The desired volume is 15 milliliters. The available formulation is 2 milliequivalent per milliliter. Okay, our units of measurement line up, so now we're ready to solve for X. (15 times 2 is 30 divided by 1, so X equals 30 milliequivalent. Alright, so pretty straightforward. Let's skip over to the units when we're dealing with insulin and take a look at those. On page 166, let's look at number 22. And this particular one's dealing with penicillin, PenVK, and it's not insulin, but that you can still use international units for other things, and penicillin is a good example. Okay, PenVK can be reconstituted to many different concentrations. You're filling an order for 175,000 units and have available concentration that has already been concentrated to 50,000 units per mil. How many milliliters is the dose? So they want to know how many milliliters do we need. So milliliters are going to be our variable. That's going to be the X. That's what we're trying to solve for. The desired dose is 175,000 units. And the available concentration is 50,000 units per 1 milliliter. Okay, so now we have our proportion ready to go. We can solve for X. The units are going to cancel out. We are going to take 175,000 times 1, which is 175,000, divided by 500,000, and that is going to give us 0.35 milliliters, which is what we're looking for. Same exact process, just a different unit. Okay, let's do one more. Number 23. Bacillin CR is given as an intramuscular injection. Preparation, it comes as 600,000 units per mil, and the dose is 1.5 million. So let's write that out. What is the volume to be administered? So volume, we're looking at milliliters. We know that's going to be X. Okay, so what is the desired dose? They flipped this particular story problem. It tells us how it comes first, but that's not going to be the desired dose. The desired dose is 1.5 million units. So that's going to go on bottom. The available concentration is 1 milliliter per 600,000 units. And now we're ready to solve for X. The units cancel. 1.5 million times 1 is 1.5 million divided by 600,000, and that is X equals 2.5 milliliters. And don't forget to write your measurement. Okay, so hopefully we went over the new units. It's still the same procedure for solving for X, so hopefully that didn't confuse you too much. If you guys do have questions, be sure to post them to the discussion Q&A, and good luck completing the rest of Chapter 6.